All right, let's dive right into one of the weirdest, most fundamental puzzles in all of physics. This is a question that really gets to the heart of what reality is even made of.
And it all comes down to this simple question. Why fractions? I mean, out of all the numbers in the universe, why are some of the most basic building blocks of everything built on a rule of thirds? It just feels so random. But what if it's not random at all?
Think about it. On the one hand, you've got particles we can actually see and hold, so to speak, like an electron. Its charge is a nice, clean, whole number, -1. Simple. But then you look at quarks, the things that make up protons and neutrons, and their charges are just strange. +2/3, -1/3. It just doesn't make any sense, right?
And to make things even stranger, get this, you can't ever find a quark on its own. It's a hard and fast rule of nature. Nobody has ever been able to isolate one. They are permanently locked up in groups. So we have two big mysteries on our hands. Why the weird fractions, and why can they never be alone?
So, where on earth do we even start to look for an answer? Well, this is where our whole explanation takes a really cool turn. The idea is that we've been looking in completely the wrong place. The secret to the quark's weirdness isn't some property inside the quark itself, but it's actually hidden in the supposedly empty space around it.
Now, to get our heads around this, we need a concept called holonomy. It sounds super complicated, but the idea is actually pretty intuitive. Imagine you walk all the way around a big hill and end up back where you started. You're at the same spot on the map, sure, but you're now at a different altitude. Your path mattered. Well, holonomy is kind of the physics version of that. When a particle moves through space, its properties get twisted by the shape of its path. It basically carries a memory of its journey.
So, how does this path memory thing explain why we have fractions? It all comes down to a very specific rule that's baked into the geometry of the void, a rule we're going to call the three-step rule. This is where the shape of empty space starts telling reality what to do.
Okay, so here's the idea. At the tiniest quantum level, space isn't perfectly smooth. It's filled with these tiny geometric gaps. And this theory suggests that quarks hang out near gaps that have the shape of a tetrahedron, a little four-sided pyramid. And that specific shape, that's the whole key.
Picture a particle's path as a string winding around one of these tetrahedral voids. After you loop it around once, its path is kind of knotted or incomplete. Loop it around a second time, and guess what? It's still knotted. But, and this is the absolute kicker, the moment you loop it a third time, everything resolves. The path becomes smooth, unknotted. The geometry of this void has a built-in rule of three.
Now, this isn't just some neat little visual trick. It's got a proper name in mathematics. This whole 3 steps and you're back to square one rule is called the Z3 group. It's a fundamental pattern that comes directly from the symmetry of that tetrahedron shape.
And right there, that's the light bulb moment. If the space itself is working on a fundamental rule of three, then any property a particle gets from moving through that space, its holonomy, has to be based on that same rule. It has to come in thirds.
And here is the beautiful payoff. This whole geometric idea translates directly into a formula from physics. The holonomy literally forces the electric charge to be chopped up into exact thirds. The shape of space is dictating the laws of physics. It's just, wow. And just look at how perfectly this works out. If you start plugging different whole numbers in for m in that formula, you don't get a bunch of random fractions. You get the exact charges we see in nature for the quarks, -1/3, +2/3. It's a perfect match.
But you might be thinking, okay, but what about electrons? What about their nice whole number charge? For this theory to be really solid, it has to explain that too. And guess what? It does. The idea is that particles like electrons live near a different kind of geometric gap, an octahedral void. The shape has a different symmetry, one that leads directly to whole number charges, like -1 for the electron.
So it paints this incredibly elegant picture. You've got different families of particles, and their most basic properties are defined by the geometry of the space they call home. Quarks live near tetrahedral voids, so they follow a rule of thirds and get fractional charges. Leptons, like electrons, live near octahedral voids, so they follow a rule of integers and get whole number charges. It's that simple.
Okay, so that just beautifully explains the whole fractional charge mystery, which brings us to our second puzzle. Why can't quarks ever be free? Well, the theory answers this with a concept called topological neutrality. And you guessed it, the solution is once again all about geometry.
Remember how we said 1 or 2 loops around the void left the path knotted and incomplete? Well,
A single, isolated quark is just like that. It carries this unresolved geometric twist, like an unbreakable string that ties it back to the void. It simply cannot exist on its own in a stable, complete state.
So how does nature fix this problem? Well, think about a proton. What's it made of? 3 quarks bound together. And what was that magic number from the void's geometry again? Yep, 3.
And here's the beautiful solution. Each of those 3 quarks is carrying its own little piece of the knotted path. But when they team up, their individual 1/3 twists add up perfectly to one complete, resolved, unknotted whole.
This finished, resolved state is what's called topological neutrality. So quark confinement isn't some mysterious force pulling them together. It's a fundamental rule of geometry. To be a free particle that can move around in the universe, you have to be topologically neutral. And for quarks, the only way to do that is to team up in 3s.
Let's just take a second to let that sink in, because the implications here are massive. This isn't just about quarks anymore. This is about the fundamental shape of reality. It suggests that the deepest rules of the universe, the ones we thought were just brute facts, might actually be consequences of pure, simple geometry.
So, what are the big takeaways here? First, the quark's fractional charge isn't some random number God picked out of a hat. It's a direct result of the threefold symmetry of space itself. Second, quark confinement isn't a jail. It's a partnership they need to be geometrically complete. And third, and this is the big one, maybe the fundamental properties of matter aren't so fundamental after all. Maybe they just emerge from the underlying shape of reality.
And that's really the idea I want to leave you with. We always think about physics in terms of forces, fields, and energy. But what if all of that is just a shadow? What if the universe's source code isn't written in equations of force, but in the pure, elegant language of shape?